Very good afternoon to all of you. Today we have Professor Niranjan Ghaisas with us. He is from IIT Hyderabad. He is a faculty there, and he has a very sort of illustrious career. He has done his PhD from Purdue University, and then he did two postdoc tenures, one at Delaware, University of Delaware, and other one at CTR, the Center for Turbulence Research at Stanford University. And right now he is faculty at IIT Hyderabad, and his research interests include fluid dynamics, of course, but mainly simulations, boundary layer processes, and his current interest is wind turbines, wind farms, and how atmospheric boundary layer processes are related to the power output from the wind farm and so on. So without much ado, I request Professor Ghaisas to please start his talk. No, you can stand here.
Hopefully I'm audible. So thanks a lot for having me over here on a fairly short notice, actually. So thanks for arranging this, and thank you for all of you showing up here. So I'll talk about our recent work over the past 2 or 3 years on incorporating surface roughness heterogeneities onto the simulations of the atmospheric boundary layer and how that affects the performance of wind turbines and wind farms. So let me start by acknowledging my PhD students, Naveen, Kingshuk, Jay, and Utkarsh. It's because they spend hours and hours in the lab is the reason why we are able to make progress to the extent that we have. Let me also thank funding from the usual SERB, National Supercomputing Mission, and also seed grant from IIT Hyderabad. Okay, so this is let's start with some numbers of wind energy. So this is a map of India with contours, and the contours represent how much wind power potential is available at a certain height. So in this case, at 100 meters above the sea, above the ground level at that particular place. And so if you add up all of these numbers together, it comes out to 300 gigawatts. So if you go 100 meters from the height, from the surface elevation, you have 300 gigawatts of harnessable power blowing in the wind, and installed capacity at the end of financial year 23 is about 43 gigawatts. Not all of it at 100 meters, most of it much lower than that. So this number is increasing fairly rapidly. And by 2030, the target is to reach about, or by 2022, the target was to reach 60 gigawatts. We're at 43 gigawatts right now, but there are ambitious targets that have been set. So the installed capacity is one thing. What is actually harnessed or what is actually feeding into the grid is a different matter. So what we see today is that total capacity factor is about 15% for most wind farms. And the penetration to the global, to the total electricity consumption of India is only about 4% right now. So the interesting aspect is that these two numbers are not very starkly different over the rest of the world. So barring some Scandinavian countries, over the rest of the world also you have similar numbers. Maybe they are better by say a factor of 2 or so, but not by an order of magnitude. Okay. So what all of this points to is, among several other things, this points to the need for studying the fundamental fluid dynamics of wind farms. So the fact that these numbers are so low is not only because of fluid mechanics, but fluid mechanics is part of the reason why these numbers are fairly low. So here is the major problem. So we have a wind turbine installed in the on the ground in the atmospheric boundary layer, and you have a turbulent inflow coming in from here. Behind the turbine, you have the turbine wake. And so if the incoming flow had this logarithmic profile, behind the turbine, you have this deficit, or you have a hole in the momentum here. So the velocity deficit or the velocity profile shows a clear deficit. And so so the wake is nothing but a region with reduced wind speed and Because of reduced wind speed, there is higher turbulence, there is higher shear, and so on. Now, you rarely have one single isolated turbine installed in the atmosphere. You generally have a cluster of turbines. So when you have a cluster of turbines, these wakes are going to interact with each other. So this is a very famous picture because it's very rare to visualize wakes in this manner. So what you see here is an offshore wind farm. This is a photo taken from a helicopter, and this was sometime in the morning hours, and the conditions were just right so that you had precipitation. You had condensation only in the wakes of these turbines and not elsewhere. So as a result, you can see behind every turbine you have a wake, and as the wake expands, you can see that this cloud is also expanding behind it. So you have this first row of turbines. Behind that first row, you see a second row here, and behind that, you probably can't see the third and fourth row, and so on. But what you can see is the wind is aligned exactly with the direction of one column of turbines, and this is going to cause trouble. If you have the wake of a turbine hitting the wake of the downstream turbine, then that degrades the performance of the downstream turbine by quite a bit. And so that performance degradation can be as high as up to 60% for particularly bad layouts and particularly bad wind directions. So there is a joke going around in the wind energy community that no presentation is complete without this picture. So now I have shown you this picture, so I've ticked that particular box. Okay, so what are these wind turbine wakes dependent on? So the primary, or what are the wind turbine wake interactions dependent on? The primary measure, or the primary quantity that affects it is the spacing between the turbines in the horizontal direction. So you have Sx in the streamwise direction. Similarly, you would have an Sy in the spanwise direction. So the primary effects are because of this horizontal spacing and the layout. How do you arrange the turbines? And also because of the incoming turbulence, the atmospheric turbulence. But you also have secondary features. So for example, you have buoyancy, you have rotation of the earth, you have surface or soil properties, and you have what is happening because of solar radiation and so on. If we look at all of these factors, each comes with their own length scale and time scale. So for example, you have the density stratification is important, say the first 250 to 500 meters from the ground, depending on what the Obukhov length is and so on. For every turbine, you have its turbine diameter, you have the turbine blade, which has a certain core thickness. Then you have this inter-turbine spacing, which is another length scale in this problem. The turbines rotate at a certain RPM, so that introduces a time scale to this problem. The Earth's rotation, the Coriolis effect caused by that has a time scale of about 1 hour. Then you have incoming solar radiation. So the surface heat fluxes, they vary with a time scale of about 1 day. And of course, you have turbulence, which is broadband, which starts from the largest to the smallest scales. So based on all of this, you have millimeters to mesoscales and you have milliseconds to years kind of affecting this problem, which makes it both challenging as well as interesting. So given this, there are several open questions related to how do you extract the maximum amount of power at minimum cost. So optimal extraction of energy is the primary question. But you also need to ask questions such as, how do you minimize the effects on the local micrometeorology, or how do you minimize wind farm noise? So costs with putting up a wind farm is not just based on the dollar amount or the actual operating and installing and operating cost. It's all these other costs also that we can contribute to in some way. Minimizing those costs can also be part of our goals for researchers in this field. Okay, so with that background, let me try to come to what I'm going to talk about in this presentation. So here you see a wind turbine, which is sited on ground, and behind that you see these salt pans or salt flats. So you have a land body here and you have a water body close to it. So you have a transition from a land surface to a water surface, and you have a wind turbine or a wind farm installed in that region. Similarly, here you have these arbitrary two-dimensional patches where you have cultivated land somewhere and you have fallow land somewhere else. So you have this wind farm, and then you have different patches with different crops, some being fallow, some being cultivated, and so on. And as a result, the surface, underlying surface in both these cases is not homogeneous. And so what we want is we want to study the effects of these surface roughness heterogeneities on the wind farm performance. And this becomes more and more important as the horizontal extent of wind farms increases. So earlier, if you just had 4 turbines, it was more likely that your underlying ground was homogeneous. But now if you have 400 turbines in a given region, then over those 20 or 30 or 50 kilometers, it's more likely that you will encounter some sort of a surface heterogeneity within that wind farm. So this is one focus area. The other focus area is what happens if your wind farms are not sited on flat terrain. So if you have a hill, or if you're rolling hills like this, or if you have slightly sharper mountain ridges or ranges here, we can see that in this case, the turbines are all lined up nicely on the crests, on the local peaks. Here you have some turbines that are not exactly on the crest. They are somewhere in the middle. So wind farms sited on uneven terrain, or what is the optimal siting of wind farms given that the underlying terrain is uneven, that is another area of focus for my research the last few years. So surface elevation changes, surface roughness heterogeneity is what we are focusing on. And what I'll talk about today is only the second part, which is surface roughness heterogeneities. And within that, I would like to talk about 3 aspects. One is just the boundary layer flow. That is the flow without any turbines, just assuming a flat surface, which undergoes surface roughness heterogeneity. Then we will talk about an isolated turbine behind a surface heterogeneity, and then we'll talk about wind farm close to a surface heterogeneity. The tool that we use is high fidelity simulations. And as you all know, they give very detailed information, but they're very, very expensive. And so what we need is that high fidelity simulations need to be accompanied by simplified model development. So these model developments or simplified analytical models are going to be suitable for design purposes. When you want to run a large ensemble of simulations, or a large number of, you want to do parameter sweeps, it's possible to do with analytical models and not with the high fidelity simulations. So I don't know what the norm is here, but if you are okay, I'm okay with being interrupted at any point and being asked questions in between. Okay, so let me talk about the LES code that we use. It is called PADEOPS iGrid. It has been under development over the last 4 or 5 years. We started developing it when I was a postdoc at Stanford with a couple of PhD students there. So what it does is it imposes realistic atmospheric conditions onto one or more wind turbines. That's the primary one-line summary of what the code does. So we use high-order numerics. We have Fourier spectral discretization in the horizontal directions, X and Y. And we have a 6th-order compact finite difference scheme in the vertical, that is Z. We use a high-order Runge-Kutta time-stepping scheme up to 4th order. Sometimes we use 3rd, sometimes 4th. And it is open source. We've made it available on GitHub. So if one of you wants to try it, you're welcome to do that. It is modular, so you can add your own modules on top of it if you want. We use modern Fortran constructs for it. And it is MPI parallel with this particular library, which 2D-comp and FFT, which allows us to scale really, really well. So there are 2 major simplifying assumptions that we have to make this problem computationally tractable. The first one is related to the turbine, and the second one is related to what happens close to the ground. So the turbine, what we say is we are interested in what happens at the wind farm scale, not at the turbine blade scale. So because we're interested in what happens over, say, a few tens of kilometers, we don't really care about the details close to the blades. So as a result, we don't exactly simulate, or we don't fully resolve the blade geometry or the shape of the tower or the shape of the nacelle. We impose body forces that mimic the action of the blade forces. So this is done through what are called actuator disk or actuator line models. So in the case of an actuator disk model, which is what we primarily use, we have a disk which represents the turbine rotor, and we impose body forces within that disk region, which affects the flow field, which in turn gives rise to the turbine wakes, which is what we are interested in studying. So this is a well-established technique, and we use that for our simulations. The other simplifying assumption that needs to be made is close to the ground, because our Reynolds numbers are at least 10 power 8, if not more. The viscous sublayer and the transition layer are very, very small, and they cannot be resolved. So what we do is we throw away the viscous terms entirely, because the viscous terms directly themselves are important only inside this region very close to the ground. And instead, what we do is we introduce a wall model. So wall modeled LES is what we are doing, and we have several wall models which I will talk about in the next few slides. So these two are major simplifying assumptions, which makes our code relevant to atmospheric conditions and not to engineering conditions, where you cannot really do these kind of simplifications. Okay, so here is a plot of the scaling. So we are scaling on, so this is the number of processors or cores. This is the number of cores, so going from 100 to about 1000. And you can see that the ideal efficiency is this dashed line, and the actual measurements that we made for how long it takes to run a problem adheres fairly well to this ideal scaling line. And we can see that we have an 82% parallel efficiency on 1000 cores. The important number is here is the granularity, which is how many points do you, how many grid points do you have per core. So we see that we get good scaling, or this particular scaling is for 61,000 points per core. So as long as your problem is that big, it will work fairly well with our code. So one good thing is that it exploits what are called these AVX 512 instructions, and all the NSM clusters, I'm assuming, including the supercomputer at IITM, has these instruction set. If it's an Intel compiler, or if your CPUs are Intel CPUs, then more often than not they have this instruction set, and that speeds up the computations really by quite a bit. So the point is that we have spent some time in the computer science aspect of the code, such that we are able to scale fairly well, and that allows us to do large problems relatively efficiently. Okay, so let me talk a bit about validation. So here is an isolated turbine exposed to a turbulent inflow coming in, and you can see that the incoming flow has some turbulence. You have a turbine which has a wake, shown by these blue regions, that is reduced wind speed. And then as you go further downstream, there is entrainment from the two sides, or from the entire three-dimensional the boundaries of the wake. And you can see that the blue gradually dissipates into yellow and so on. So the wake is recovering as you go downstream, far away from the turbine. If you take a slice, or if you take a line across the center line at different distances downstream of the turbine, you will get a deficit in the velocity like this. And we can see that the our LES is agreeing fairly well with wind tunnel experiments that are shown by the symbols here. So this is the mean velocity. This is the turbulence intensity. You can see that the turbulence intensity peaks close to the top tip of the turbine. And our LES also captures that peak and also agrees fairly well with the rest of the entire profile is predicted fairly well. So this is shown only at one location, but we have measurements at several different locations, and it all agrees quite well, except for very close to the turbine. Here is a relatively recent validation that we've done. So this is for flow over a nice smooth Gaussian hill without a turbine. And you can see that you have flow coming in from the left, and you have a hill wake here. You have a recirculation, and you have a wake that is caused by the hill. And there is a shear layer here, and you can see that the flow structures are nicely resolved. And this is in good agreement with experiments also, as we see here. So here we are comparing the vertical profiles of the streamwise velocity, the time average streamwise velocity. And here we are comparing the turbulence intensity at different locations with respect to crest or the top of the hill. And we can see that there is good agreement for both these quantities as well. We can now move on to very large wind farms. So this is 10 turbine rows and 3 turbine columns. And as you can see, this is exposed again to a fully turbulent inflow. And you can see that behind each turbine, you have turbine wake. And these, in this case, the turbines are placed close to each other in such a way that before the wake of a turbine recovers to a great extent, the next turbine is encountered. Okay, so you can see that this blue region is affecting the turbine wakes are interacting with each other, and you can see the wakes meandering as they should, because these deficits are sort of modulated by the atmospheric boundary layer, which has much larger length scales compared to the scale of the turbine.
Can I ask something?
Sure, yeah.
So this movie is being shown at the center of the disk at that height?
Yes, yes. Yeah, so this is a plan form. You're looking at the plan view. X is the streamwise, Y is the spanwise, and you have this is at the turbine hub height. Yeah.
So the incoming turbulence is random?
It's not random. So we have a precursor simulation. We have a simulation with exactly this dimension, which is just the boundary layer. And what we do is we take data from there and feed it in as an inflow. So it has all the length scales, the correlations, everything as per boundary layer turbulence is imposed at this inflow.
May I ask, in the LES code, so how do you treat the boundaries? Are they like radiating outward the solutions?
Do you mean the streamwise boundary?
Yeah.
Yeah.
No,
So
I mean, you have a partition box kind of system, right? LES.
Yes, yes.
So the flow has to come in and then leave.
Correct.
So how do you impose these radiating conditions?
Correct.
Radiating, are they?
Right. So what we have is we don't have inflow, outflow. We have a periodic boundary conditions in the X and Y. So in both horizontal directions, we have periodic conditions. So to mimic inflow, outflow, what we do is, if this is my region of interest, I augment the domain here. And then we impose, so this is like a fringe region. And there I copy the field from the precursor into this.
Like a cyclic.
It's cyclic, yes. Yes. It is cyclic.
There is no shock or anything. Continuously.
Yes. So it's periodic or it's cyclic, but we add an extra forcing term here, such that the flow here is nudged to the flow in an undisturbed boundary layer, where there are no turbines. So as a result, what you get here is you don't see any signature of any wakes in the upstream. Yeah. If we don't do this, if we try to go for an inflow outflow, as you said, the radiation boundary condition or an outflow boundary condition is a big challenge. In incompressible simulations, especially, it is a big challenge. And secondly, we won't be able to go to spectral methods in the horizontal. If it's not periodic, if it's not periodic, then we will have to use a finite difference scheme there also.
And this is solely spectral.
In horizontal, it is spectral. Yes. So this is the qualitative picture. And then again, if we take mean velocities at different locations downstream, behind different rows. For example, this is behind row 4. This is behind row 7. And then these are turbulence intensities at those same locations. You can see that the solid blue are our LES, and the non-filled circles, these are experimental measurements, or these are wind tunnel experimental measurements. So we have good agreement there also. So the point is, this is well validated over several different studies, starting from about 2017 and right up till 2024. So we continue, whenever we build a new capability, we make sure that it is extensively validated. And so full quantitative validation is very, very important. Okay, so with this, let me come to what I'm going to talk about in this in the presentation. So first of all, I talk about simply the boundary layer flow without a turbine, but with the surface roughness heterogeneity. And in that, I want to talk about 3 things. One is the major challenge, that is wall modeling, and then the LES results following that. And then analytical models for the mean velocity and the turbulence intensity that I talk about. Okay, so here is the simplest problem that you can think of. So let's say you have a surface with a certain aerodynamic roughness height, Z01, and that surface abruptly transitions to a surface with an aerodynamic height, roughness height of Z02. And this transition is abrupt. It is perpendicular to the direction of the mean wind. And the question now is, what will be the surface shear stress? What will be the velocity profiles? What will be the turbulent intensity or other turbulent statistics, and so on in this region here? So this can, for example, represent a transition from land to sea, the coastline, where you have a mean direction to the wind flow, and then you have a coastline which is sort of perpendicular to the mean wind direction. And this is an idealized model of that situation. So the major challenge is how do you impose the wall model at the lowest, at the bottom wall. So what is the wall model? The question with a wall model, or the purpose of a wall model, is given the instantaneous Elias filtered velocity field at the lowest grid point in your computational domain at a certain position, what is the flux, or what is the shear stress that you impose at the bottom wall? So as I described earlier, this is because this needs to be introduced because we're throwing away the viscous terms because the viscous sublayer is very, very small. So conventionally, what people have used is they've used the equilibrium log law, and they've inverted that log law to get to the wall shear stress. So for example, the mean velocity is this log law here. There is a friction velocity, and then there is the logarithmic dependence with the aerodynamic roughness Z01 here. If you invert that and solve for U*1, or you solve for the friction velocity, you get this formula. And how this is used is that you now apply this, although this is in terms of average quantities, you apply this at every instantaneous point. So you take the instantaneous velocity field, you average it in x and y, that becomes the numerator here. Then you divide it by this, and that gives you the friction velocity at the bottom wall, and that value is applied everywhere in the domain. So this sort of an approach works, or these log law based wall models, these work when your surface is homogeneous, because you have to use this averaging here. And so these log law models will work here, but they will not work here, because what you now have is you don't have the surface being homogeneous when you are downstream of an abrupt change. So here we need modified wall models, or we need a different wall modeling approach. So there are there are two options that people have. So this problem was realized fairly long ago, and then there are two options for heterogeneous surface wall models that have been proposed in the literature. So one is what I'm going to call the BZ wall model, based on what the author's name is. This was proposed in 2004, and the idea was that instead of using the Elias filtered velocity field, you use a 2 delta filtered Elias velocity field. So if your Elias grid size is delta, you filter that velocity field by a filter of width 2 delta, and you use that 2 delta filtered velocity field in exactly the same manner as you would in the equilibrium wall model with the Elias filtered velocity field. And the reason given for this was that 2 delta filtered velocity field is hopefully going to be less weakly tied to the lower surface than the Elias filtered velocity field. So this is like a hand wavy sort of an argument, and that's what they proposed. Another one was proposed in 2013, and where the idea was to, instead of using a 2 delta filtered field, you still use the Elias filtered field, which is at length scale delta, but now you average it in span. You use a span-wise averaged velocity field, but you also do a linear combination between the upstream and the far downstream. So so this formula is a bit hard to decode, but let me try to do that for you. So there is a weighting function lambda, When this lambda is 0, you have far downstream conditions, and you apply essentially the same model that BZ applies. Okay, so if lambda is 0, then you just have something similar to what you see here. But when you are upstream, as you approach the upstream, lambda goes to 1, and this doesn't exactly become singular, but you can see that you have 1 minus lambda in the denominator. But this numerator is also approaching 0. So you don't have a singularity, but the idea is that you're essentially doing a linear combination between the conditions far upstream and far downstream through this weighting function lambda, and you use that to develop or to propose what the friction velocity should be and what the wall shear stress at any given point should be. So there are these two candidates for wall models that have been proposed in the literature. And what we did was we applied those, and then we got some results. So with that in place, we are able to do a rough to smooth transition So here you can see a rough patch of a certain length. Then the surface roughness transitions to Z02, which is smaller than Z01. And then you have a smooth patch, and you can hopefully see that the region of blue is slightly reduced over the smooth patch. So you have a certain acceleration as you go from rough to smooth surface. This is the opposite situation where you have a smooth to rough transition. And here you can see that there is a larger region of blue compared to what you have here. So we are able to do both. And so these are qualitative pictures, but if we try to do this more quantitatively, we can resort to benchmark experiments. So Chamorro and Portegel performed these experiments in 2009. And here is a picture from their paper. They have a transition from a rough region upstream to a smooth region downstream, schematically shown here. And then they did measurements at all these different stations with respect to the point of the transition. And these are wind tunnel experiments, so they are well controlled, and we have good quality benchmark data to compare against. So this is what our results look like. So you have the wall shear stress plotted against the streamwise distance. And because you're going from a rough to smooth transition, the shear stress downstream of the abrupt change is going to be less than 1. So this is the wall shear stress tau divided by the wall shear stress upstream of the transition. And because you're going from a rough to smooth, these values have to be less than 1, because the next surface is, the second surface is smoother, and as a result, the shear stress is going to be smaller. So what we see is that the Bouzaid wall model with different grid resolutions is sort of okay. It is as you refine the grid, it is approaching the level of the experiments. The Apkar wall model is slightly better, or is significantly better than the Bouzaid wall model. But there are some issues with the Apkar wall model also. So for example, as you refine the grid, you can see that it is actually the shear stress predicted is actually going down, which is not kind of expected. So we can see that the wall shear stress is very, very sensitive to the wall model and the grid size. Here is a profile of the mean velocity. The mean velocity profiles are not as sensitive to the wall model as the wall shear stress values are, and they're in reasonable agreement with the wind tunnel experiments. So overall, we can conclude that both of these are fairly good. Apkar model is better. Bouzaid wall model, if you have good enough resolution, it will be quite as it will approach the experimental results as well. Okay, so a few more insight that we get into the problem from the LES. So we see the formation of an internal boundary layer height. So whenever you have an abrupt rough to smooth transition or a smooth to rough transition, the effect of the surface roughness, the changed surface roughness, is felt by the flow in a gradual manner. So very close to the surface roughness change, only a small region is affected by the changed surface roughness, and this height of this internal region that sees the changed surface roughness grows as you go further and further downstream. So that is quantified in terms of this internal boundary layer height, delta I. And the internal boundary layer height more or less grows monotonically with distance from the surface roughness jump. And there is an empirical relation that was proposed way back in the 1950s, and that agrees fairly well, at least for this particular case, with our LES results. Another bit of insight that we see is if you plot the U prime W prime, the momentum flux as a function of the vertical height, upstream of the surface roughness jump, you have a straight line that goes all the way to -1, because this is the normalized momentum, the normalized stress. And when you have a surface roughness jump, downstream of the surface roughness jump, you have it following the straight line, and then you have the momentum, the U prime W prime adjusting to the new surface. So for the rough surface, it would approach a magnitude of 1. For the smoother surface, it's going to approach a magnitude which is smaller than 1. And the interesting bit is that the U prime W prime here is also in this portion inside the IBL. It is linear. So these two pieces of information is what we get from the LES. That's going to help us in the analytical model development. So let me talk about analytical model development for mean velocity and the wall shear stress. So this is our schematic. We have a sort of abrupt transition here, and we want to ask whether we can predict these three quantities in a simple manner without resorting to full simulations. So here's a quick recap of what existed previously. So the same paper that put out these experiments, Chamorro and Portageon in 2009. So here they are plotting the wall shear stress normalized by the upstream wall shear stress as a function of the streamwise distance. The measurements are here. And what they showed was previous studies. One was Elliott's model in 1958. Another was this Panofsky and Townsend study in 1964. These are completely under predicting the wall shear stress. In 2009, they proposed a new model, and it was in better agreement than these two. But you can see that it is slightly diverging as you go further and further downstream. And also, this is only a prognostic model. This is this is only a diagnostic model. This is not fully predictive for reasons that I don't want to go into. But this model requires you to know the velocity itself to begin with, which makes it which doesn't make it very useful. So we have two models which are bad. We have a model which is reasonable but not fully predictive. So this is the point where we started from. In the next two slides, I'm going to describe how we derived the how we derived the analytical model for the mean velocity here. So we start with this picture upstream of the step change. We have a region that is in equilibrium. So what I mean by equilibrium is that we have a constant wall shear stress, or the total shear stress, the tau is a function of z, is the same that it has has the same value as at the wall. So the shear stress is minus u star 1 squared. U star 1 is the friction velocity upstream of the step jump. An equilibrium boundary layer is one where you have the eddy viscosity being proportional to the height or the distance to the wall. So nu t is proportional to z. And if we make these two assumptions, we get a du dz, which is 1 by z, and that gives you a log law, right? So this is one way of deriving the log law, and this is applicable in the upstream region. The question is what happens downstream. So the downstream, we assume that the region is divided into three layers. We have the internal boundary layer, above which you have the equilibrium conditions from the upstream persisting. So you have an equilibrium layer 1, which has this similar log law as you had in the inflow. Then very close to the wall, you have an equilibrium boundary layer, which is a second equilibrium layer. And then again, you will have a log law. And then we assume a transition layer between this lower log law and the upper log law, lower equilibrium layer and the upper equilibrium layer. And what assumptions to make for the transition layer is what we resort to the LES for. What the LES showed us was that tau as a function of z is linear and not constant within the transition layer. So we assume that tau is proportional to z rather than being constant. And the one further assumption that we made was that the eddy viscosity nu t, or the turbulent viscosity, is the equilibrium viscosity, which is proportional to z plus an augmentation. And the major assumption that we made was that the augmentation is going to be parabolic. So we assume that the turbulent viscosity is essentially a parabola, az plus bz square. With this sort of an assumption in place, once again we get a modified log law. So with these two assumptions, which are motivated from the LES results, what we get is equations of this sort. So we have the final expressions are in the first equilibrium layer, we have a log law with a roughness of Z0 1, that is the upstream, that is applicable outside the internal boundary layer, far away from the lower wall. The second equilibrium layer is applicable very close to the changed the wall with the changed surface roughness, that is here. And in the transition or matching layer, we have an expression which is a closed form expression for u of z, which can be derived using a simple pen and paper. So the good thing about this entire model is that it is fully predictive up to two parameters. The two parameters are alpha, which is the height of the second equilibrium layer to the height of the first equilibrium layer, So height of this inner layer to the height of the internal boundary layer. The second parameter is beta, which is the degree of nonlinearity of the eddy viscosity augmentation. So when beta is 0, you again have a linear eddy viscosity. When beta is non-zero, you have a parabolic profile for the eddy viscosity. So I'm not showing that here, but we've also empirically proposed the appropriate range of values for these alpha and beta, which allows us to make predictions for a wide range of boundary layers. So here is the picture that I'd shown you previously. Previous model predictions were here. The diagnostic model predictions were much better than previously, but they were diverging as you went farther away, farther into the boundary layer. And the blue line here shows our predictions, which are in fairly close agreement with the experiments. Similarly, this is for a smooth to rough transition. So now you have the wall shear stress being greater than 1 when normalized by the upstream, because you're now going from a smoother wall to a rougher wall. And again, we see that our model is fairly good at predicting these observations. And these are the wall shear stress values, but we can also predict the full velocity profiles. So again, for some smooth to rough experiments, we can see that we're able to predict the velocity profile quite well at different places, at different distances downstream of the wall. Okay, so let me talk about the second part, or the third part, which is analytical modeling for the turbulence intensity. So as we all know, turbulence intensity is important for, say, second order design. So for example, if you want to quantify the fatigue loading on turbine blades or noise predictions and so on, that's when the second order turbulence statistics become important. So previously, there have been empirical formulas that have been proposed for homogeneously rough surfaces. So one example is what is called the reverse log law, which is essentially saying that U prime, the streamwise fluctuations, they are given by this reverse log law with two empirical constants, A and B, and ln of z by delta, where delta is the total boundary layer height. So this is purely empirical, and this has been used by tweaking A and B, you can essentially fit the velocity, the turbulent fluctuations profile. However, there are no, at least to my knowledge, no previous either empirical or theoretical formulas available for the turbulence intensity over heterogeneously rough surfaces. So when you have a heterogeneity in the surface roughness, there are no existing formulas available. So what we did was, again, we resorted to our LES and made a very simple observation. The observation is that the turbulence intensity downstream of a surface roughness jump, so for example, this profile here at x by delta equal to 1, gradually moves from the TI profile far upstream to TI profile far downstream. So the TI profile far upstream is this blue line here. That is a TI profile for a homogeneously rough surface with a surface roughness Z01. If you have a homogeneously rough surface with surface roughness Z02, you would have this TI profile. And what we observe is as the distance from the surface roughness jump changes, x by delta equal to 1, 2, and 3, we can see that this profile is gradually moving from the blue line to the red line, or so the blue line to this, whatever this line is. Okay, so the idea was that we express the turbulence intensity as a weighted average between upstream and far downstream. So Ti is a weighting function phi times Ti far downstream plus 1 minus phi times Ti upstream of the surface roughness jump. And Ti far downstream is given by Z02, surface roughness Z02, and Ti upstream is given by surface roughness Z01. So we developed a phenomenological model for this weighting function phi, which is given here. And if we evaluate the model for this phi here, we see that it agrees fairly well with the LES. And when we put it all together, we evaluate the model for Ti, that is, we evaluate this expression for Ti with phi given here. We can see that the turbulence intensity also is predicted quite well downstream of surface roughness jump by this very simple analytical model. Okay, so that brings me to the end of my discussion on the boundary layer flow. The rest two I'm going to talk about are an isolated turbine and a wind farm. And I'll be fairly quick about these two because I've covered this one in a fair bit of depth. These two I'm going to sort of go much quicker than the first one. Okay, so here is what we're interested in. We have, let's say you have a surface with roughness Z01, and then there is an abrupt surface roughness transition to Z02. And what happens if you install a turbine downstream of this surface roughness jump? So we're interested in studying the effect of the heterogeneity on the wind turbine wake. And to compare this, we consider two reference configurations. One is that we remove the heterogeneity. So we have a homogeneously rough surface with surface roughness Z01 everywhere. And the second is that we remove the turbine. So we have a surface roughness heterogeneity, but the turbine is removed from here. So our primary interest is in this configuration, but I'm going to compare it to these two reference configurations as well. So this is what the time average contours look like. So we have a surface roughness jump here. And as a result, the region of blue slowly vanishes. The flow accelerates because of the roughness being transitioning from a higher value to lower value. You see the same thing here. And wherever you have a turbine, you have a turbine wake.
Analytical solution, right?
Sorry?
Analytical solution.
No, these are LES now. We're back to LES now. So these are LES and these are time averaged results from an LES.
Why are they so smooth here?
Because they are time averaged. Yeah. So if the time averaging duration is long enough, then the fluctuations will die out. So we can see that there is a turbine wake here and a turbine wake here, and we can see that there are qualitatively significant differences between the velocity deficit here and the velocity deficit here, which is just reflective of the fact that your underlying surface roughness has changed from a high value to a low value. We can then quantify the surface roughness or the effect of the surface roughness in terms of different quantities, say the mean velocity or the velocity deficit and so on. I'm not going to spend time on this one. So finally, what is important for developing analytical models or for predicting power is the velocity deficit. So if we take the velocity deficit is usually defined as the profile, velocity profile upstream of the turbine minus the velocity profile downstream of the turbine. So if I have a turbine here and if I take the velocity profile, say 1D upstream and subtract the profile somewhere in the wake of the turbine, we will get the velocity deficit. What we see is when you have a homogeneously rough surface, this velocity deficit profile works fine. But when you have a heterogeneously rough surface, because the velocity is accelerating, we end up getting a negative deficit here. So if you look at this line, red line here, you can see that it is becoming negative close to the wall. And that is directly a consequence of the fact that close to the wall, you have an acceleration because of the change in surface roughness. Now, the velocity deficit going negative is problematic because we would like to model this using a Gaussian shape. So as you can see, this shape has sort of a Gaussian feature. There is a peak, and then you have e power minus r square kind of decay on either side of the peak. But e power minus r square, as we all know, doesn't go negative. And if your deficit is going negative here, then that's a problem. We cannot model this. We cannot approximate this function by a Gaussian function. So what we did was we came up with an alternate definition of velocity deficit. So what I'm calling a new definition of velocity deficit, and that new definition is delta u is u from the second configuration that we studied minus the third configuration. So just to recall, the second configuration was the surface roughness jump without a turbine, and the third configuration is surface roughness jump with a turbine. So the new definition of velocity deficit now is the deficit here is the profile here minus the profile here. Earlier, the definition was the profile here minus the profile here, which is going negative. And if I now use this as the reference profile and subtract this from here, we get a positive definition of, or we get a positive deficit. So the new definition of velocity deficit, delta u, as you can see, is only slightly negative, and here it is more or less positive. So this new definition delta u is amenable to modeling rather than the older definition du. Okay, so essentially what we've done is we've changed the definition of upstream in calculating the velocity, or we've changed what is considered as upstream in calculating the velocity deficit, and that gives us a new definition of deficit delta U. When you change the definition of upstream, the upstream itself is changing in X. Previously, what was used here was only a function of Z. It was not a function of X. Now we have this quantity, which is a function of X, and that requires us to rework the definition of rework the derivation of what previous models had used. So previous models, particularly the model of Bastankha and Portagel, which was proposed in 2015, that worked only when your upstream velocity was not a function of X. So we've now reworked that derivation, and that gives rise to new terms. We have 1 minus f of x term here. This f of x is new, and this additional factor gamma, which is also new, and this last term here, which is also new. So if we put f of x to be equal to 0, if we put gamma equal to 0, and if we ignore this particular term, we reduce to the model of Bastankha in 2015. And because our velocity here is a function of x and z, we have to introduce these additional terms as well. But once again, we have a nice analytical expression which can be evaluated, millions of times that you would need for doing design studies. So just to quantify what the new model does, so here we have LES results. This is the velocity deficit as a function of distance from the turbine. And you can see that the velocity deficit starts out large, and then it reduces as you go, as the wake recovers, it reduces in magnitude. And we can see that the older model was agreeing only after, say, 6 diameters. The new model is agreeing right up to the location of the turbine. Similarly, if you take the radial profile at a certain station, so this is at 2D, so at 2 diameters downstream of the turbine, if you take the radial profile, we see that our model again is agreeing much better with the LES than the previously developed model. Okay, so that is for modeling a single turbine, the wake of a single turbine. Let me quickly talk about multiple turbines. So now we have, instead of one single turbine, we have 10 rows and 3 columns. And again, we are going to study this configuration, which is of interest to us, but we have several of these reference configurations. One is where we remove the turbines, we retain the heterogeneity. One is where we remove the heterogeneity, but we retain the turbines. And once again, we see the exact same observations that we had shown for a single turbine, which is that the old definition, that is du, ends up going negative, as you can see here, here and here. And the new definition, delta u, does not go negative. The new definition continues to remain positive at almost all locations. So we can model the new definition of deficit delta u rather than the old definition du. So without much details, we have developed a model chain. The first step in the model chain is the boundary layer flow model. That is, without the turbines, only the boundary layer, only the step change in surface roughness. What is the background velocity profile there? On top of that, we impose the model for an isolated turbine that we published in 2022, and then we couple all of these to wake merging models. Wake merging models, we've tried out several. The one that works best is this, that was again published in 2022, not by us but by others. So if we combine these all these 3 pieces together, we can come up with maps of this sort. So this is the mean streamwise, streamwise velocity in the plane of one of the turbine columns. And as you can see, the effect of the turbines increases gradually. And behind every turbine, you have wakes, those multiple wakes merge into each other using this model and so on. So this is the qualitative picture that we can generate. And if we quantitatively see what it looks like, this is the evolution of the velocity deficit in the streamwise direction. Wherever you have a turbine, the velocity deficit jumps. Then as you move further downstream, the deficit goes down. As soon as you encounter another turbine, it jumps again. So you have this kind of a pattern. You have a recovery in this portion. Then a second turbine is encountered, so the deficit jumps again. Then you have a recovery again, and so on. So you have this exact kind of a pattern. and our model evaluated for different kinds of the different parameter values, different parameter ranges, different tunable parameter combinations. That gives us this kind of a picture. So you can see that we are somewhere in the range. Of course, there will be good model combinations and more bad value combinations, but that is something that you can play with it very, very cheaply.
How is this deficit recovered? By entrainment of
by entrainment, yes. By entrainment from all sides, it recovers.
Photograph you have shown that looked like it was strengthening.
So as it spreads, the magnitude actually reduces. So as the radial extent spreads, if you look at the center line, the values go down, which is what you see here. So as this goes down, the radius is going to expand. Okay, so this is what the velocity deficit looks like, and then this is what the power prediction looks like. So we have the LES results here. The first turbine is generating the most power, and the second turbine is generating less power than the first, and so on. So what we see is that our model or some appropriate combination of the model parameters gives us the ability to reproduce these LES results quite well. And this is shown for one particular combination of design parameters. So for example, this is xt, sx, and zt equal to whatever these numbers are. And once we've tuned our analytical model with our LES results, we can then do some design studies. So for example, what we see here is I'm changing xt, which is the location of the first turbine from the surface roughness jump, while keeping the others the same. So the zt is the turbine hub height, and sx is the streamwise spacing between the adjacent turbine rows. So we keep these two fixed, change the distance of the first turbine. So essentially, we move the wind farm closer or farther away from the surface of this jump, from the shore, from your shoreline, so to say. And what we see is that for different cases, the LES and the analytical model agrees quite well with each other. Okay, so to summarize, what we've done is, or what I've tried to convey to you is that LES is an invaluable tool for studying both boundary layers as well as wind farms. And it is important in developing simplified analytical models, which will then be used for design studies. So we've currently investigated effects of complex terrain, primarily surface roughness heterogeneities and uneven terrain. So when it comes to surface roughness heterogeneities, the first challenge is what is an appropriate wall model, and we've overcome that to some extent by looking at two available choices and comparing to the experiments and picking up which one works best. Then we've done LES-aided development of models for the mean velocity, for the shear stress, and the turbulence intensity in the boundary layer without turbines. And we've also done the same for predicting the mean velocity or the velocity deficit and the power of wind farms for both an isolated turbine as well as aligned wind farms. But there are lots of open questions related to how do you operate these wind farms optimally, or how do you further better design for different parameters. Okay, so thanks a lot. I can take any questions that you may have. Thanks.
I have a question.
Yeah.
Thank you for this very informative talk. So I have a question which is more related to the climatology or the kind of work that we do here.
Yeah.
Thank you. So this is regarding the pollinators and the movement of pollens actually. If you have a large scale wind farm, then most of the wind energy is actually taken up by these farms to generate the energy. What happens to the pollinator movement or the pollens that are carried by this wind? And as you were showing, there can be an ecotone, there can be a change in the surface type, there can be an agricultural farm beyond that, fallow land or something, or the forest. So do you think, or if you think, then how much the effect of this will be on the productivity of that, pollinators and pollens?
Right. So particularly pollinators or pollens, I am not aware of at what height do they generally do they move. A typical wind turbine hub height is say 100 meters, and the diameter is also say 100 meters. So the wind tip is say between say 30 meters to about 150 meters. That would be the dimensions of a wind turbine. larger animals, such as say bats, for example, the birds or bats, there are concerns about them hitting these turbine blade or being hit by turbine blades and then actually perishing because of that. But particularly in terms of pollinators, I'm not aware.
Even if your blade height is quite high, let's say 100 meter or something, with a diameter of 30 meter, as you were saying, but beyond that, in the upstream of the wind, actually, it is creating the wake, which will kind of force some material to go down towards the surface, isn't it?
Yes.
So even if they're flowing closer to the surface, there might be some additional term which is forcing them down. That's what my understanding is.
Right. So I mean, if you want to consider them as passive scalars, passive scalar transport will be affected by these wind farms. It is quite a bit affected by wind farms. Also,
so you are talking about pollen grains which are carried by the wind,
right? And the pollinators.
Yeah. So passive scalar mixing is definitely modulated. Both primarily you bring stuff from bottom to top. Right. That's what happens with wind farms.
Thank you.
Any further questions?
I have one question, sir.
Switched off.
So now my question is that this LES looks very promising and comparing excellent with the model versus the LES. So, but we, the scientists who work in the fluid, which is atmosphere or the water ocean, we always look for some similarity between these two, what we are resolving in our scale. The question is, this is LES done on a neutrally stratified fluid, but when we come to the stratified fluid, this logarithmic profile and all won't hold there. So how we can adapt that into a realistic situation that we face in our boundary layer? So that is my question.
Right.
So what would be in other words, what would be the effect of convection on this and the diurnal cycles and so on, right?
Yeah, one way of putting it is that way. The other way, the simplest question is how the stratification would alter this results.
Right, correct. So, so there has been a fair bit of work on incorporating density stratification or thermal stratification into this. And typically, what we see is when you have convective conditions, the ambient turbulence is larger, and as a result, the wakes recover faster. And as a result, the effect of the upstream turbine on the downstream turbine is reduced. So this drop that you see, that will be weaker if you have this drop here, this drop between the first and then this one. So this will be weaker if you have convective conditions. And if you have stable conditions, then the wake of every turbine persists longer. So you have a stronger, you have a larger drop because of upstream turbines. How do we incorporate that in heterogeneity effects that into surface roughness heterogeneities that?
So in the current model of your LES, you can't have that gradients of variables in dimension.
In the LES, we can.
Okay.
The code has the potential, can solve a potential temperature equation and has a Bosnian term which will affect the momentum also.
Mm-hmm.
So the code can solve it. We are working on that also.
Oh, I see.
The analytical modeling, I haven't gone to that part. Right now we're only doing neutrally stratified conditions in the modeling part.
Okay, so we would be naturally interested, as Shivasai said, how the convection can be parameterized, learning from the experiments of LES.
Right.
And that how we can carry up to the scale that we want, which is the atmosphere, because that's one of the biggest challenges in all the atmospheric models which forecast precipitation, etc.
Right.
So that's what we have. That's our interest. That's why I asked that question. Thank you.
I have a question.
Rather question, there is one query that in your model, LEC model and wall model, you have considered the turbine height, which is a constant. Suppose velocity deficit is a concern. Why there is a varying height of the turbine, starting from the shorter height to larger height? This can you comment on that?
So you mean to say, what if you have turbine hub heights which are not the same, but they're going up or down or consistently going up or something like that? Yeah. So I mean, theoretically, people have done those kinds of studies. People have looked at what is the best way of. So when you do optimization studies in the layout, people have also done optimizing the vertical height is another parameter. But practically, what happens is the turbine, you just design one turbine with a certain tower structure and certain blade characteristics and all that. And for maintenance purposes, for operational purposes, it helps if you have uniformity. So if the way airlines, some airlines prefer to run only one model of an aircraft. Similarly, for operational purposes, one wind farm is typically composed only of one model of a wind turbine. But yeah, theoretically, people have done those kinds of studies where you arrange turbines in a zigzag pattern, or whether two turbines should be of the same height and the third should be taller, or one should be smaller. There are lots of theoretical studies of that sort.
Add something here.
Yeah.
So in fact, actually, few weeks back, we had presentation by Professor. In fact, few weeks back, we had presentation by Professor Somnath Boidoray from IIT Delhi, and he also talked of something similar to this wind farm optimization and all, and he covered a bit on these different structures and arrays of the wind turbines, basically. Yeah.
Yeah, he works on larger scale problems, right? But yeah, what is probably of more interest to IIT, or direct interest to IIT?
More towards the climate and wind and
Right.
sustainability perspectives. Yeah.
Any other questions? Okay. Okay, then I think let us let us thank Professor Ghaisas for nice talk, and
Okay, thanks a
let's
lot.
now join for the tea
Thanks.
quickly. Thank you.
Stay.